Hello, everyone, and welcome to another meeting of our conversational AI reading group. Today, we are very happy to have another great speaker, Samuele Cornell from CMU, talking about conversational speech processing challenges and opportunities. If you have any question during the talk, please feel free to raise your hand or drop the question in the chat. Without any further delay, the stage is all yours.
Yeah, thanks. Yeah. Just interrupt me. As the presentation goes. So yeah, thanks for the introduction. And yeah, by the way, the important stuff first, oh wait, yes, happy birthday, Mirko. I think I saw on the LinkedIn. Maybe I don't know if it's your birthday, but I thought it was.
Thank you. Thank you. It's
It's your
actually
birthday?
40. Yeah,
Yeah. Oh, wow. Okay. That's an important date. Yeah. Happy birthday
yeah.
then. The important
That
thing
is
first.
in the middle of the semester, but yeah, thank you. Thank you very much.
Yeah. And so, yeah, let's get more serious, maybe. Yeah, I'll go. That's how my presentation is structured. I will give a brief introduction on what is speech in the wild, speech processing, what's conversational speech processing, and what's the current state of the art, and then present two works. So one is about end-to-end meeting transcription, so how to avoid modular pipelines and cascading errors, and the other is how we can simulate data because like we don't have much data for some scenarios. And lastly, I would give some current and future directions, like some current work I have and some directions that I think are interesting for the field. So yeah, what's speech in the wild? It's basically speech processing that we try in my research. I try to address the everyday speech. No, we forget about sometimes we think about speech processing as a human machine interaction or now with LLMs and so on. But speech is social phenomena. It's chaotic. You usually we used to communicate to each other. It's usually two or more people involved, and you have colloquial terms, your dialect, you have overlap speech, people interrupting each other, and so on. And it's also long form, right? When we interact with Siri or Google or whatever, we have keyword spotting, so we know the segmentation. But like with spontaneous interaction, it can be 15 minutes, it can be 5 minutes, it can be 1 hour of talking, of people talking with each other. And usually it's captured by far-field microphone devices. So this means that you will get more noise, you will get more overlapped speech, and so on. To give you one example, this is like Chime 6 data set on which I worked with Mirko, I think back in 2019 in Montreal, by the way. And I've been working on this area for the past 6 years, maybe too much. And to give you an idea, this is like a dinner party scenario, so it's very chaotic. People like could speak to each other, and so on. It's for people. And this is one example captured from a far-field microphone device. They are raised in the picture.
I didn't know how many tomatoes to get, so yeah,
I think two is
like one, maybe one per person.
So yeah, there are people like they're cooking, and it's very noisy, right? And this is the close.
I didn't know how many tomatoes to get, so I got like 4. Like one, maybe one per person. A lot of tomatoes.
So you have like the far field and then the closed talk, which is what I don't know, like your algorithm, like for example, a speech enhancement would like to get. And this is like a cocktail party phenomenon, it's called. And we are all familiar with this. Humans are very good at this. Like we somehow can understand each other in poster sessions where it's I don't know, like 50% talking at the same time, and we still make sense out of it. And the machines cannot do that right now. For example, for hearing aids is a huge problem. Like we would like hearing aids to work to be very robust in this situation, like poster sessions or like a restaurant and so on. I have a friend that actually has hearing aids and goes to conferences, and he has trouble to, like, for example, in the poster session or like real-time translation. we don't think about it, but if we want real-time translation in the real world, like in a busy street, in a market, in some foreign country, you need to address this multi-speaker, noisy speech problem. So to me, it's like this is a fundamental problem. We don't most modern AI, I think it's too much text-centric because text is the most data we can get in the web right now is text. And but language is evolved for multi-speaker interaction, and the text is a technology. So text is we shouldn't we should we should think more. Text is actually a technology, and the language is it basically evolved from spoken interaction. So it's more a fundamental problem. And the current AI is mostly text-centric. So despite the efforts, like you have Gemini that claims that they can process audio, even long form audio, conversational speech, and so on. But like, for example, for paralinguistics, like I don't know, speaker identity or like emotion and so on, it's actually quite bad. So I think it's a problem is related to representation learning in some way because most of the training data is still text. And then you do supervised fine tuning with some maybe interleave or like some pre-training after like the main pre-training on text. But basically, it's a representation learning. I think like speaker identity is fundamentally mismatched with text-based representation because how you describe absolute speaker identity, like a speaker embedding vector, for example, which represents absolute speaker identity with text terms and so on. I think it's very difficult. And this is why, for example, in my opinion, the paralinguistic is actually very hard with the current paradigm unless we change the training data from the beginning, from the start. So also to me, it's exciting this research area of conversational speech processing because I think we should move beyond human-machine interaction, which has its place, like assistive technologies and so on. And LLMs are pretty useful, and so sometimes we don't want to type, but sometimes we want to speak to them. It's quite cool. But like I think it's also there is quite some there is also a risk that we end up in human machine bubbles like the movie Air because these days with interspeech deadline I pretty much spend more time chatting with Claude than my friends probably. So I think it would be cool to have also conversational AI agents that can handle conversation with multiple people. So they can understand our messy human-to-human conversation and integrate with I don't know better in our work environment. Like for example, robots. For a robot, you need to like a robot in a restaurant, for example, or for healthcare applications, it needs to address different people and so on. So it needs to understand the sound scene. And I think big tech is not very focused right now on this, and it's a great opportunity for academia for this kind of multi-speaker conversational AI agents and so on. So where we are right now, like I don't know, I mostly focus on this talk on meeting transcription, but it also applies to other tasks like speech separation, speech enhancement. So where is big tech, right? That maybe they're not focused on it. Maybe they are more focused on single human to machine interaction. You know about the OpenAI Whisper. It's trained on 5 million hours of weekly labeled, probably mostly YouTube data. And in the paper, and it's claimed that it's competitive better than the human, and it surely is, like on mostly like Libre speech, common voice, and so on. But also like on this the Chime 6 data that you listen to it, which is very noisy, multi-speaker, 2 hours long, messy. They claim it's actually very competitive. So end of my talk, right? It's a solved problem. It's OpenAI solved it. But actually, like if you read the fine print, what they use to compute these metrics is Oracle segmentation and diarization. And I told you like we don't have like in the real world we don't have for spontaneous interaction. We need to do diarization. We need to do segmentation and so on. And also they use very old school techniques such as beamforming, for example, which is, yeah, like they use very like classical techniques actually, not very DNN based or very fancy new techniques. So yeah, the problem is this segmentation. The segmentation is very difficult. Like when you have few minutes to hours of data, and you need to segment the data, you need to identify the speakers, and then you can apply your ASR model. Maybe you can identify the speakers, identify the start and stop of each utterance, and so on. And then you can apply speech separation, and then afterwards you can feed it to the ASR model like Whisper, and then you get a decent result. But this long-term information tracking to identify the speaker identities, for example, is quite difficult. So, like, I don't know, what about LLMs? Right? Like Gemini 2.5 Pro, it claims it can do like multi-speaker transcription with hours of data. And if you feed like AMI meeting data, which is 25 years old, and it's not very difficult, it's like just an office meeting, not too noisy and so on. The result is pretty bad. Like it's with 10 minutes only, the realizational rate is 79%, and the full length is almost everything is an error. And for yeah, like if you compare with open source state-of-the-art system, which is 10%, so they completely misattribute the speaker identities. And of course, like this is a big problem because if you want a transcription system that is useful in the real world, it's important who said what and when, right? It's otherwise not very useful. And this problem is related, I think, to the length of the sequence, which is for 1 hour is 110K tokens, which is huge. And to the fact that the data is not that much. So a whole meeting becomes one training example for your model. And maybe you can collect thousands of hours. Maybe if you are Google, like tens of thousands of hours and so on, but it doesn't suffice. And finally, like you have an autoregressive system. And so like it's very prone to error accumulation. So if you have an error, for example, in the timestamps or like in the speaker IDs and so on, the model is very prone to accumulate those errors. And what it happens is that we observe like for Gemini, some of the timestamps and like after the audio boundary. So the audio is like 10 minutes. The model says that there is speech, someone said something at 15 minutes and so on. So it goes beyond the boundary. And for some domain, this is not a problem. You don't have this problem. Like Zoom meeting, you have a channel for each speaker. So you have Oracle diarization and separation. You have one stream, and this model works perfectly. But like again, like with far-field spontaneous interaction, it's another story. And what you need to do is just use a modular system. And this like it's right now it's the state of the art. And even like Whisper, in their paper, like they use the modular system with Oracle information, which is even more powerful in some sense. So like yeah. You have this very complex pipeline. And if you look at the current state of the art results, like we run these challenges like the CHIME 7 and 8 distant ASR challenges. We had 4 different scenarios with different with very different like recording setup, number of speakers, duration, and so on to make it very challenging. And we measure the performance not only for diarization and segmentation about segmentation, but also speaker attribution and then recognition with this time constraint minimum permutation order rate, which is a special order rate for long form audio. And we found out that we had quite some participants in these challenges. It was pretty cool. And the participants were able to improve on this on basically Whisper with Oracle diarization and this guided source separation. So they were Whisper using Oracle information. We were able to beat it, which is pretty cool with a real system because Oracle is not real. right? So, but still, like for example, the best system achieves a macro TCP word rate of 20%, which means 1 out of 5 words is wrong, and the whisper is 1 out of 3 words is wrong, even with Oracle information. So I think the task is not solved at all. So it's quite challenging, and plus you have this very complex pipeline, which is actually more complex, because like for example, for these submissions in the challenge, which are quite amazing, uh, like in terms of performance, but also quite amazing in terms of engineering, because they have like tens of components, which is difficult to optimize, and in a real deployment scenario is maybe suboptimal, but challenges with strive for performance. So, but yeah, like we would like to maybe simplify the pipeline, for example. So I don't know, maybe the long-term vision is to try to do this end-to-end meeting transcription, and I tried to do that in the past. And the idea is, okay, if you have this end-to-end meeting transcription, maybe you can improve, right? Because you can have cascading errors. So if you have a very complex pipeline and you have like a question.
Yeah, so maybe one important question is
Yeah.
what is the Oracle diarization here?
Oh, it's just Oracle segmentation. So you given basically you see the speaker tags. So like you have a long form audio, and you are given the segmentation already. So you already given the speaker ID, and then the start and stop of each utterance, and so on. Instead, if you don't have it, just have a long stream audio, and then okay, you need to see how many speakers are in this meeting, where they are speaking, and so on, and then you can feed to the ESR system. So like Libri speech, for example, is already pre-segmented because it's an audiobook, right? But like if you are talking with your friends and for 1 hour, it's not segmented. Somebody has to do the segmentation. Somebody has to count the number of speakers, and then has to. You need to develop a system, and that is the job of like the digitalization system over a year, pretty much. And then you can feed to speech separation. You separate the streams for each speaker, and then you can feed to ASR. So yeah, and the thing is that okay, if the organization makes an error, like it estimates wrongly the number of speakers, then the error trickles down to the whole pipeline, right? Because you estimate the number of speakers wrong, and then the whole pipeline is broken. So end-to-end meeting transcription, the promise is that okay, maybe you don't have this problem, so you can optimize it end-to-end. And I made an attempt when I started my postdoc, and I was able to achieve a quasi end-to-end in some sense, and only single channel, not multi-channel system. And the idea was to basically train an attention-based encoder-decoder system to do end-to-end meeting transcription, but only at the local level. So at each window of 20 seconds, you can train an encoder-decoder model, like based on WaveLM plus you train a decoder to estimate this kind of output. So speaker 0, time, the sentence, the end of the sentence, timestamp, and so on. And this it's end to end, right? You can train this like on each window. Why on each window? Because it was very difficult. So one is like a computation, like your memory constraints, and the other is like it can basically generalize to an arbitrary number of speakers. So the idea is like we have 20-second windows, and for each window we can enforce some constraints. Like since the model is applied to each window independently, you need to apply the speakers. These speaker tags are only relative to the current window. So you need to enforce a convention. Like for example, speaker 0 is always the speaker that speaks first in the current window, and speaker 1 is the second, and so on. But in the next window, it may be different, right? Because the model has no context from the previous window. It's applied independently to each window. And you can do this like local end-to-end meeting transcription, right? But then you need a mechanism to keep track of the global speaker IDs. And this is actually what we did is just use clustering for that, because then yeah, what I told about like Gemini and so on, like this is very difficult to have a model to train on a very long sequences. You need lots of data. You need 10K meeting, for example, and so on, because each example becomes one training example. In this way, it's just at the window level. And so we just train the model encoder, so which is based on WebLM, to have another speaker ID output head, which we trained with a contrastive loss to estimate speaker embeddings for each speaker for each local window. So for each local window, we get this local output plus speaker ID vectors.
There is one question in the
Yeah.
chat. Is there a reason why 20 seconds was the duration selected for the window?
Yeah, there is no reason except I had a 140 gigabyte GPUs and I had to use that. So yeah, you can definitely, I think the performance will improve if you go longer window, 100%. So yeah, you should use longer windows if you can. Then of course, like if you start with a model like Whisper, which is limited to 30 seconds, also probably for the same reason, for training efficiency. Yeah, you are stuck with 30 seconds. But if you can train from scratch, you should use 1 minute, maybe 5 minutes, and so on. And so yeah, the idea is just you have for each window you also have speaker ID vectors, and then you can use the clustering to basically resolve the global speaker assignment. And this was so we trained we did our experiments on this AMI meeting corpora, where I showed that Gemini, for example, is totally unable to do anything. The performance is quite bad still. So yeah, and yeah, I will not go into the details. We measured the performance by idealization rate, which measures speaker attribution and temporal localization for each utterance, and then the concatenated minimum permutation order rate, which measures instead the recognition and the speaker attribution. And we were able to match pretty much this transcripted rise, which was Microsoft work, and yeah, like it was close, but the catch was we have only one training component, so one trainable component only. They had the VAD, then the realization, then target speaker ASR, which is 3 trainable components. So it's conceptually simpler. You can make that argument, but yeah, like also it's very far from the state of the art, which is right now in the state of the art quite improved thanks to Alex. These actually are. Also, I am a co-author of this, but this like so the modular system still win. And I think we should be honest. I don't think maybe it's not more robust. So I said that there are no cascading errors, but we are doing joint modeling of the realization and an ASR. And I think they may fail in the same way. Like, for example, the ASR may fail due to dialectal speech or heavy accented speech like mine. And then this can trickle down to the dearization, right? The timestamp estimation. So we don't know if actually it's more robust, but it's definitely simpler in some way. And another thing is that you need lots of data for these systems, like because it's end to end. So you need data that is labeled with multi-speaker labels, and so. This data is very costly to obtain, and we have very few, like few thousand hours of English and Mandarin data jointly, not that much, at least open source. So I tried to.
Okay, maybe before going further, there are two questions in the chat that
Okay.
is kind of related to training data. So have you considered generating such long hours of data synthetically instead by
Yeah.
stitching multiple individual clip of the same speaker?
Yeah, that's what I will. That's the other part of the talk.
Okay.
Yeah, and it works. Yeah, so I used actually. I used it. It's still not enough. So you can generate synthetic data, but I'll talk a bit right now
Okay.
about the challenges of that. Yes.
Okay, perfect. And maybe the last question in the chat. Could the failure of end-to-end system to handle diarization be partly attributed to the lack of accurate alignment?
Uh, yeah. I think yeah, I don't know what you mean about alignment, but I think the supervised data we have quite accurate alignment. I think that it's a data problem in some sense that the realization needs we need it's very costly to annotate and we don't have much annotation. So like it's quite difficult because it's very difficult to even for humans it's quite difficult if you close your eyes, you listen to a podcast of 4 or 5 people, and then you have to track, oh, how many speakers there are, who said what. It's kind of it's not easy. So yeah, I think there are many different directions one can try, like trying to, I don't know, pseudo labeling some YouTube data, for example, with the dearization system, maybe audio visual, and then you get better pseudo labels. But right now, open source data is not much, so that's probably one of the main reasons why. And then yes, of course, end-to-end systems like Gemini and so on, the context is too long, I think, and they just break because of that. But I'll talk more about that maybe
Yes.
later. Yeah.
Maybe there's one more question. What are the primary failure modes of the diarization? Is it the right words at the wrong time? Is it the timing is slightly off, or maybe 3 seconds too late?
I think mainly it's okay, like for Gemini, it's speaker attribution. Like more than 2 speakers, it doesn't handle very greatly. And then the timestamps are completely off. For other system, again, it's they are more precise. I will talk about later, like end-to-end system based on LLMs. But the speaker attribution in again, like far field data, more than 2 speakers, it's quite bad. Still very quite bad. 2 speakers we can address. I think it's a data problem. Most of the data we can find out there, like telephone speech, Zoom call, and so on, it's 2 speakers. So
Perfect.
yeah. So yeah, so like about simulation, for example, for some scenarios, we cannot collect any data, like doctor-patient, for example. It's private, very for privacy reason we cannot collect. Also, multi-channel data, it's impossible almost. Like even if you look at the ODAS and so on, we can get very few examples with more than 2 channels. And we can have some stereo data, but most of the stereo it's not great maybe. So and to collect this kind of annotation like meeting data, you need very specialized recording setups. It takes quite a long time to annotate because you have to listen to each speaker stream independently and transcribe it. So what we do is you simulate data, right? And I did for the end-to-end system. I simulated the alpha data was simulated in this way. You just cut, paste, and mix with some toolkit, right? You just take a library speech, you mix it together, you mix some noise, you reverberate, and there are several toolkits like the Nemo one. I used the Nemo one at the time. But the problem is that, of course, like it's not semantically coherent. Right? It's very many people like reading different stuff in the same room in some way, and then the turn taking is very bad. So it's quite not realistic enough. And what about TTS? We can use TTS, and there are some previous work that use TTS for single speaker case, but we can extend very easily for multi-speaker, right? You just generate each speaker independently and just sum them. And this is still unrealistic in the turn taking, but at least we can control the content, so it can be semantically coherent. So this is one
In like
example.
what's
Yeah,
going
like
on.
we're sitting there, and you're like, what's going on? And am like I don't know, man. I think we're just
Yeah, like we're just
don't know.
So it doesn't sound like a conversation. It sounds like everybody's reading again, but at least you can control the content. So what we try to do is just we had this idea about training a TDS system to generate directly multi-speaker speech. And then the idea was, okay, once you have that, you can use LLMs, which are trained on conversational speech transcript, because you can take, they see like Reddit conversation, Twitter conversation, which are quite similar to real world conversation in some way. And then we can use that to generate fake conversation and then generate fake multi-speaker TTS data. And then we can use this data for adapting ASR models and so on. Like for doctor-patient conversation, for example, you can use the LLM to generate doctor-patient transcripts and then generate with a TTS system a fake recording. But the catch is that you need to train a TTS system to output two speakers or multi-speaker speech directly. And this, like my colleague Jordan Dareski from University of Rochester, is what he did. He came up with this Parakit conversational TTS system, which is basically DAC-based, so it's like autoregressive system on neural codec tokens. And they can generate two-speaker conversation of 20 seconds. So it's still limited, but it served our purpose in this work. And we trained this on the Spotify podcast dataset, which is 60K hours. And the interesting stuff is that basically he used the Whisper large VT to pseudo-label this corpora, just to fine-tune on 200 utterances with manually annotated data in this way. So speaker one, sentence, speaker two, sentence. It did the job pretty well. So I think it's very efficient because Whisper was trained on YouTube, and YouTube is very similar to this format. So yeah, and then once we had this conversational TTS system, and which has some advantages, right? Now we can have a semantic coherence because we can control the content, and we can have also realistic turn taking and multi-speaker interaction. And of course, it's slower to simulate, but we can make it pretty fast. So, and this is one example. So the transcript is also generated from my LLM, and that the audio is also fake.
I'm like, what's going on?
Yeah, like we're sitting there and you're like, what's going on? And I'm like, I don't know, man. I think we're just, I don't know. Like, what are we doing, man?
Yeah, like we're just sitting there, man.
So the cool stuff is that basically the model also learns to use the suspension dots or like question marks and so on, or the commas. Like he learns like to where to give emphasis and the conversational flow. So it's very realistic, this type of conversation. And so we tested this kind of multi-speaker TDS, this whole pipeline on the Fisher corpora for telephone speech and another corpora, Mixer 6. And the idea was like, okay, now we test how this data, how good it is for adapting an ASR model. And we use Whisper. So we adapt Whisper on these fake conversations to get some multi-speaker ASR model. And of course, like the top line is to use in-domain data from Fisher. So 2000 hours, 80 hours, and so on. This is like the best results possible, right? You can collect 2000 hours of in-domain speech data with multi-speaker data. And the other is a NEMO multi-speaker simulator, which is the cut and paste from LibreSpeech. And of course, like it degrades, like you have 34% CPU error rate. And then the other baseline is XTTS, which is okay. You just feed. You don't have a conversational TTS, but use a TTS system independently for each speaker. And again, it degrades. It particularly degrades if we use LLM generated transcript. So LLM random is using LLM generated transcript to feed to XTTS. If you use the original transcript, like from Fisher, it's 24, but with LLM1 it grades because I think it's the TTS system is not used to see conversational like transcript. So the cool thing is that with our model, it doesn't degrade the performance with LLM generated transcript, which is I think is even a little bit better. So it means that we can control the conversation, like which is it's quite cool because like for some domains you can inject some specific terms, and it significantly surpassed the other methods, especially with the LLM generated transcription. But you have diminishing returns. So if you double the amount of data, 20 to 19.9, it's so there is a cap you reach. And this was for telephone speech. Now, what about far field to speakers data? For this particular domain, you can only get 2.30 hours of transcription of training data. And actually was annotated by myself, Matthew Wisner, and so on. So it was very painful. Like to annotate the data set, which was few hours, I spent like 2 days. It's very painful. So this is more realistic domain, realistic deployment scenario. And if you use Fisher, you can obtain very close performance. But also, the cool stuff is that okay, the simulated data works almost as good as Fisher. So this I think it's pretty powerful. Like the synthetic data works as good as Fisher, which is telephone speech, for another domain, which is Mixer 6, which is far field data. So it's basically as good as real data from another domain. So and the results are pretty good. Like with 80 hours, we can match the Mixer 6 2 hours in domain data, almost. So it kind of works pretty good. And of course, like there is limitations. So with our conversational TTS system, like it generates the mixed audio directly. It would be nice if it can generate for each speaker the independent audio. So you can use for training a separation model or the relation model. And also it's trained on podcast. So it means that, if you want to generate reverberation or noisy speech, you still go back to the classical way of reverberating speech, mixing noise and so on. And what about the multi-channel? It's not addressed. Also, you need probably to generate a duplex output for that one. And it's quite difficult. It's a chicken and egg problem in some way. So you don't have much data for duplex output, like at all. Like Spotify podcast data is not duplex, so you don't have the separate streams. You have telephone speech, which is mostly duplex, but it's only 2 speakers, and also the quality is not great. And yeah, multi-channel is a huge problem. So, any questions on this or no? We can.
I think there is one question. It is,
Okay.
could you please explain what is the CP word error rate? Is
Oh,
it
yeah.
generally used in multi-speaker diarization ASR?
It's basically it measures the it measures the speaker assignment and the recognition. You basically for each speaker stream you concatenate the hypothesis, and then you take the minimum the permutation, you compute the word error rate, and then you take the permutation that minimize the word error rate, because diarization it's permutation invariant problem, so it requires you don't know the original permutation, so you need to try all the possible permutation for the speaker assignment, and then you take the minimum. So yes, it measures speaker attribution and recognition, but not segmentation errors. So yeah. Like what about multi-channel? I think for multi-channel probably we have to use in my opinion a different approach. Like data is very scarce, like for hearing aids and so on, data is very scarce. So in my opinion, we need to learn on device for this kind of task. So And it's possible if we can devise a self-supervised learning objective, and it's simple enough that it can be performed on device. So I came up with this spatial joint embedding prediction architecture, which is from Jan LeCun JEPA work. It's heavily inspired by that. So the idea is that you are in a restaurant or like in this EasyCom dataset scenario where you can have a smart glasses or hearing aids, and then there are multiple speakers around and so on, and multiple sound sources. And many people don't know, but lots of devices, even the pods I have here right now, they have an inertial measurement unit, so they can track their movement. So we have information about the movement of the array system. And the idea is we can use that to enforce a SSL objective for sound localization. So the idea is like we know when the array moved, right? So we can take and we have the waveform. We have the waveform. We know when the array moved. So we can take two snapshots before the array moved and after the array moved. Compute spatial features like interchannel phase differences. And then we can feed these features to an encoder model. And then we can enforce some consistency, which is the classical joint embedding predictive architecture consistency. So the student model, given the information about the movement, should be able to predict the teacher representation. So it should be able to predict how the sound scene moved, the sound scene changes given the movement, right? And the only way possible to do this is to basically disentangle the sound information. So for example, the direction of arrival from each sound source, because then it becomes trivial, the problem. Like you just put an offset to the angle of from where the sound arrived, right? Like in this figure. So you know how much the array rotated, and so if you know the original direction of arrival, you just rotate by the same amount. So this forces the model to disentangle the representation of the sound scene. And with that, I have some preliminary results. This is like a work in progress. I just too much stuff for interspeech right now. But yeah, we test this on the EasyCom dataset where people use smart glasses from Meta. And we have Oracle information about each speaker location. And the interesting stuff is that we can achieve basically on par performance with this M-Bester Q model, which is however like 100 million parameters, and our model is 200K parameters. So you can train on device in this way. So that's the idea. So I think it's for multi-channel, we need to train on device because if you scrape from YouTube and so on, there is not much training data at all. Like maybe a few thousand hours of real multi-channel audio, like from a Meta can do it maybe because they have their devices. But for academia and so on, it's very difficult to acquire multi-channel conversational data. And yeah, finally, I go quickly about this. So I go back to the end-to-end transcription system results as before. I talked, like I have this end-to-end meeting transcription. It's pretty good, but still, like the modular system are much better still. And now everything changed in the sense that I showed some example of Omni models like Gemini, but also in the last 2 months there are these like Vivoice ASR, which is an end-to-end system based on LLMs. And Vivoice is actually pretty good. Like if you look at these results, which are again on AMI data, and I compute the diarization rate and the CPU order rate. So diarization measures the segmentation, the speaker attribution, CPU order rate measures the speaker attribution and the recognition. It's still far from the modular systems, but it starts to be quite good. The Gemini models, they're actually getting worse, and they cannot do long form. These results are not with long form processing. These are with chunking. You do the chunking as in my approach, and then you do the clustering. Because if you do long form, the results are 100%. And this LLM-based approach, the Viboys system, it can do long form. So it can process like, I think 1 hour of data. So it's actually pretty good. But I think there is a catch. So these systems, we know we want LLM-based system because of flexibility, right? We would like to do summarization. We would like to do question answering and so on. And you can do that with Gemini and so on. But you are forced to do chunking right now for these systems, which defeats the purpose because then you cannot do summarization, you cannot do question answering. It's back to a cascaded system. So it defeats the purpose of using a Omni model to use the chunking. While instead these specialized LLM-based systems, they can do very long form processing and they somewhat robust, but still much less robust than modular systems, especially in very challenging scenarios. But they lose all the LLM capabilities. So they are so fine-tuned to end-to-end meeting transcription that they cannot do summarization, they cannot do a question answer, they can only do transcription. So they are back to basically a conventional system, even if they start with LLMs. And to me, I think it's very interesting. I don't know, to explore this. I think there is a tension, right, from a generative task like summarization, question answering, and then verbatim long form transcription. I think like Gemini and so on, like they are generative system. They are trained with next token prediction, and then after I don't know 100K tokens, they really want to hallucinate. And so while these systems like LLM-based, like PyPoise, they are so fine-tuned that, okay, they just don't hallucinate, but then they lose the capability of summarization, which actually you need to hallucinate to do the summarization in some sense, because LLMs are hallucination machines. It's you ask an LLM to write your email, I don't know, the non-hallucinated response will be, I cannot do that. But no, they hallucinate the response. They hallucinate the answer. So even if they don't know enough context, they just give you the answer, right? So in my opinion, we get probably to some hybrid model where maybe we need to do like a cloud code for long form audience understanding, where you have your Omni LLM model that you can just code a tool, do diarization, then the diarization, returns some segmentation. The model can use this segmentation and the user query and also the audio to, I don't know, maybe apply so that I don't focus on the silent portions. So you can just make the audio shorter, for example, to drop the silence portions and so on. And so then maybe you can feed the audio again to the Omni model, or like you can focus only on some parts of the meeting that are interesting for the user query. And the nice part is that you can train the whole pipeline with reinforcement learning with variable rewards, for example, because if it's a question answering task, you can just have a variable reward. So I think we will get in this direction. Maybe not this year, but maybe in the next years. I feel that this probably is the correct approach to, like in coding and so on, to address the long form problem of also audio. It's just have an agent that can call tools and have different queries to different part of the audio, and then you optimize the whole pipeline with the functional learning. So yeah, I think that's it. Maybe yeah, I think I'm on time still.
Yeah.
Yeah. So if you have
Yeah.
any questions, yeah, thanks. And I don't know, good luck for interspeech to everybody, which
Okay,
it's a very
cool.
busy week.
Yeah, cool. Thanks a lot for the great talk. I would like to ask the audience if they have any questions, please share them in the chat or raise their hand to ask the questions. So maybe I ask one question myself, like in any of this diarization, most of the time the data set is English. How is
Yeah,
the effect if you have multilingual? Like,
that's
what is
a
the?
good question. That's a very good question. For conventional idealization, like it's mostly paralinguistic task, right? It's like getting the speaker ID, and it's actually quite language independent and very robust to accent and so on. But
Mhm,
as I said, like end-to-end systems, they do joint modeling of ASR and diarization.
mhm,
So they may be quite less robust to
mhm,
this language. I don't think there are studies in this, but my intuition is that this actually could be a very cool study. My intuition is
mhm,
that the end-to-end system are more brittle because they do joint modeling of ASR and diarization. So if the ASR fails and you get maybe
mhm.
hallucinations, then also the diarization also fails.
I
So
see.
while conventional diarization, they just do segmentation and they are somewhat robust. Uh,
I see.
yeah,
And
I don't know.
maybe
It
I
would
have,
be cool to have
yeah,
a benchmarking on this.
yeah, and maybe I have like very general question about diarization. When we do diarization, when some voice or a speech overlaps, do
Yeah.
we consider the effect that what happen if one voice is stronger than the others, like more louder? Like, is this kind of factors considered in the diarization and the effect or not?
No, like you need to. I think like you need to you need to estimate also the other speaker, like it just
Mm-hmm.
the activity for the other speaker, especially if you want to separate and then recognize the both.
Mm-hmm.
So or just don't, maybe you throw away the overlapped speech, which is also another technique,
I
because
see.
the overlapped speech will contaminate the ESR model,
I see.
right?
I
For
see.
example. So yeah, it's it has an effect, of course. Like I think it's more challenging, right? If
Mm-hmm. Yeah, exactly.
and also very challenging it's also very challenging back channels and so on. Like when you say and so those are
Mm-hmm.
very difficult to theorize or
Yeah,
to
yeah, for
separate,
sure. I see.
but they
I
can
see.
still break a bit the ISR model. So
I
they can
see.
still make you know they still break the flow of the ISR model. So you want to
I
maybe
see.
separate or ignore. And
So maybe
end-to-end
for
system,
end-to-end, yeah, exactly. I want to
yeah,
say maybe for end-to-end, this case would be easier.
yeah, it's easier. They just don't they ignore. Like by voice, it ignores the overlapped speech, it ignores also
Okay.
these kind of things. But I don't know, like if you are interested, for example, in dialogue models, actually, if you want to train a dialogue model, and you need lots of data to train a dialogue model, like and for this data, it needs to be duplex, it needs
Mm-hmm.
to have a good ASR notation, and for
I
that,
see.
you want to retain
I
the back
see.
channels and so on because they are important.
I,
The dialogue model should learn how to speak as a human.
I
But then
see.
your ASR model, your derivation models are very bad
Mm-hmm.
at getting these, and so
Mm-hmm.
you have a problem.
I
And you,
see.
of course, you don't want to pay persons to annotate 100K hours of
Mm-hmm.
speech. You would like
Makes
to
sense.
get away with pseudo annotation,
I
but
see.
we
Makes sense.
currently it's very difficult.
I see. Cool.
So
So I
yeah.
think there are two more questions in the chat. The agent-based audio understanding is super interesting. If you have any early works on that, could you please talk
Yeah.
about it?
We have a work submitted at ARR. So, but I think many people are working on this. I know at least another group that's working on this. I think it's very natural direction.
Mhm.
The problem is that the computation could be very heavy, especially if you want to do reinforcement learning. It's quite heavy. Like you need lots of you basically you get with verifiable rewards. You get one bit of information maybe, or maybe you get a score, so which is more
Mm,
informative. But still, you need to run the whole pipeline of to get that,
I see.
and then you get one reward.
I see.
So you need to spend lots of compute, I think,
Mm,
for this. But industry can do it. I mean, I don't know why they didn't do it yet, but maybe they're not interested. But definitely, it will get there, in my opinion.
mhm. Okay. Another question is, I think you mentioned SSL features in your slide. What role can they play in diarization?
I think the state of the art right now it's like with the Horizon. So it's a work from Beauty, and the work is it's quite. I mean, I think it was quite quite obvious. Nobody did it, and they did it, and they have the state of the art model. So they really optimize it. But it's. I mean, it's they use WaveLM, and the results are pretty good. Like nobody was using WaveLM, and they just beat everybody by using WaveLM. So yeah, we should use SSL feature for dealization, of course. Um, I think there is something to gain there, like in the fact that most SSL now it's I think it's too oriented towards ASR because it's masked language modeling basically. Maybe for some paralinguistic task like theorization is not the optimal strategy. But you need to come up with some strategy, like maybe you can mix audio with some other audio, and then you come up with some mask language modeling strategy that you have to reconstruct both audios and so on. So it does implicit separation in some way, and in that way, maybe you have better speaker aware representation. Because you need to separate speaker and dearization in some way it's related to separation because I think we humans theorize also by separating in some way because you listen to the stream and you attend to this speaker, then you attend to the other speaker. Oh, there are two speakers, and you keep track of the speakers during the conversation. So I think it's a very interesting problem, and especially if you can come up with a SSL strategy that is better than WaveLM for dearization. I think it's very few people are working on that, but I think it's maybe low-hanging fruit, maybe
cool.
difficult.
Yeah. So maybe last question from the audience. Jem, do you want to ask?
Yeah.
Yes. Thank you, Samuele, for a great talk. Just a very quick question about this slide, actually. So here, like you mentioned, rewards, right? So the rewards are what are the rewards basically? Are they
You can use most of you have transcripts, right? So you can verify the rewards, like it's verifiable, like they do on coding or math. You can verify the solution, so it could be like question answering, like you have a question like I don't know, like who is the speaker who is speaking from 0 to 5 seconds. The user query could be, and the reward could be like the correct speaker ID. So it's a 0 or 1 if the model misses.
yes,
And
yes. Yeah, I mean, I meant like for diarization, basically. Like
um,
that would be
the,
timestamps, I guess. The rewards on timestamps.
yeah, it could be a timestamp. It could be so the
Uh-huh.
idea is just like try. You can do whatever you can do as coding agents are doing. It can be also the order rate, for example. Order rate
Uh-huh.
could be a reward.
Uh-huh. Sure, sure.
It could be it could be anything you can think of that is variable with given the transcript. Or the motion. So the model, the idea is you can call tools. So
Sure.
like they're doing in also audiovisual task they are doing. Like this tool calling is pretty powerful. So and it's more. I think it's for example for dearization. I think it's more efficient to call a tool than feed 100K tokens to Gemini and so on. Just call a tool, give a rough idea of what's there in the transcription in the audio, and then you can drop silence because maybe the user query is not related to the non-speech part. You drop the silence then, and then at least you can maybe from 100K tokens you get half because you drop the silence.
Mhm.
Or maybe the question is related to one particular speaker, and so you can drop all the other speakers, and then the context becomes much shorter, which models like Gemini or like Quen, they can handle short, or Audio Flamingo, they can handle short context, like maybe 5 minutes, they're pretty good. You go to 30 minutes, they just do very terrible. So
Yeah.
yeah, I think it's I don't know. This tool calling is pretty cool to do.
Yeah. Yeah. Agreed.
Okay,
Thanks.
perfect. Thank you again for the great talk. Thank you everyone for joining. Next week announcement, we have Yiben Shao from Tencent AI Lab talking about where is the GPT moment for audio. Thank you everyone for joining and looking forward to meeting you all next week.